Hello, I'm Marv Candleman. You've seen me in such fine quality chemistry educational videos as "He blew up the lab, now what?" Or "Is pH of the acid really necessary to know about?" Today we're going to be looking at determining rate laws. Okay? And in our last episode, we talked about the different types of rate laws that there are, differential versus integrated. And the idea behind differential, we just simply looked at the concentration. Here in integrated rate law, we're looking at concentration and depending that on time. Okay? But how in the world do we go and start determining the rate law for an equation? Well, the first thing we got to do is look at the form of the rate law, especially its order. Okay, well, what do we mean by the order? Well, the proportion, the rate we would have, but we need to find what would be the K, our constant value, and what exponents do the concentrations of the reactants need to be lifted up to in order to make that work. But the thing is, again, you can't look at a chemical equation and be able to tell. So we have to determine that from experimental data, which means we're going to have to actually determine the actual data as far as what happens. So, the idea behind that, ladies and gentlemen, we're going to go ahead and we're going to skip down to the method of initial rates. So the idea is we're going to have to run the reaction several times. And the initial concentrations of the reactants are varied because we need to see what's going to happen. And then, of course, the reaction rate, we measure it just after the reactants are mixed together. Well, why are we measuring just after the reactants are mixed together? Because we don't want to deal with the reverse reaction. It eliminates that effect of the reverse reaction. So here we go, number one. What is the rate law and the rate constant value when the temperature is negative 10 Celsius for the following chemical reaction? 2NO plus Cl2 gets us 2NoCl. So, that's nice, they gave us the negative 10 degrees Celsius, okay, but we need to find the rate law first. And the rate law, okay, so here's our rate, is equal to some proportionality constant K. That's what we need, multiplied by the concentrations of the reactants themselves. So let's say if we had a decomposition reaction, all right, instead of dealing with one bracket to the X, and instead of dealing with two brackets like we have here, you only would deal with one, okay? So there's our rate, and it's going to be NO to the X power times Cl2 to the Y power. Remember the brackets, they refer to the concentration, specifically molar concentration. So, we need to find what the X, Y, and K are. That's what we mean by determining the rate law. We can't find K without finding the X and the Y first. So how do we find the X and Y? We need a data table to show us the experiment. And here it is. Here's our experiment for our data table. Okay, so we have our trials here, and if you notice here, it's the same concentration of both reactants. We got 0.18 moles per liter times seconds. Here in the second one, we varied. We added a little bit more Cl2, and the little O's that you're seeing there, that refers to initial reaction. That's what you initially started with. And then our initial rate is 0.36. Here, for trial number 3, we made the concentrations of the reactants equal, and then we got an initial rate of 1.45. What is that telling us? Well, we need to find X. So what we need to do, we need to pick out two trials where the concentration of NO changes, but the Cl2 concentration doesn't. Well, wait a minute. Why? Because we're trying to find how much of a power do we raise the concentration of the NO2. Do we raise it to the 2, the 3rd, the 4th, that kind of thing. And we can't have the Cl2 changing, because if it changes, we can't figure out what this one is, you see. So trials number 2 and 3, let's take a quick look here. So trials number 2 and 3, if you notice, here we have 0.20 for the Cl2 and 0.20. Yes, fantastic. There's no change here, But we do have a change here, which is the change in the NO from 0.1 to 0.2. That is perfect for what we need to do to find what is the X, the NO, the concentration of NO to the X power. That's what we need. That's what we absolutely need. So, trials 2 and 3 are perfect. But why are they perfect? Because the NO concentration changes. The Cl2 concentration doesn't. So now we can look at the rate of trial 3 over the rate of trial 2. Now you'd say, but wait, why trial 3 over trial 2? Because trial 3 is the bigger number. Okay, you always want to do that. And that's going to equal, according to the rate, it's the proportionality constant K times the concentration of NO to the X power times the concentration of the Cl2 to the Y power. And we'll do the same thing for rate of trial number 2. Same idea. Now, the really cool part is that the K's can cancel out because anything over itself is 1. Okay? And the Cl2 to the Y, they get to cancel each other out because they are the same concentration. They don't change, which means it doesn't matter what the value of the Cl2 is. If it's 0.1 or 0.15, it doesn't matter because anything over itself is 1, that basic algebra component. So that eliminates that. That eliminates that. Oh my gosh, look what we have left. We have the NOx here and the NOx here. And the thing is, guys, we know that these aren't the same. They change because we looked at that. So we can plug in the numbers. We get these rates from trial 3 and trial 2. Where did they come from? They came from this table here. Here's trial number 2, 0.36. Trial number 3, 1.45. So we go in and we look at that. Okay, so again, we're left with, the K's are canceled out, the Cl2 to the Y power, that cancels out, so we have 1.45 divided by 0.36, which is equal to 0.2 to the X power divided by 0.1 to the X power. Let's go ahead and divide it. So we end up getting 1.45 divided by 0.36 is equal to 4, which is equal to 0.2 to the X divided by 0.1 to the X. That itself is going to equal 2, so 4 is equal to 2 to the X. 2 to what power is going to equal 4? X has to equal 2. Yes! We found it. And of course I put the happy face there to prove my point. So, okay, we found X. X is 2. Yay! What does that mean? Well, it tells us that it gives us a piece to the puzzle of our rate law here. So we have our rate is equal to K times NO to the second power times Cl2 to the Y power. So what is that telling us? What's telling us is that if the rate of concentration of let me rephrase that. The concentration of NO doubles, then the rate itself is quadrupled. Wow. So, if rate is 1 and NO is equal to 1, okay, but when NO is equal to 2, the rate is equal to 4. It has a major impact on the rate of the reaction. So now we've got to figure out, what about Y? We need to find Y. So we're going to pick 2 trials where the Cl2 concentration changes, but the NO concentration does not. Okay, that would be a big thing. So we go back to our trials here, we go back to our trial here, and we look, our Cl2 changes, there we go, 0.2 and 1.1, and our NOs don't change, so we flipped. We flipped from finding what the X was, now we're trying to find the Y. Now remember here, the 0 means initial, what you started with for the concentration. So now we can go back down here, and this will be a little bit easier because we know that the K cancels out. The NO squared cancels out, yes. So that leaves us with the rates of the 2 trials and the concentration of the Cl2s to the Y power. So now we can go ahead and let's plug those bad boys in. Okay? And again, I'm showing you step by step how that works out. This goes away. Okay, the NOs, really, the NOs cancel each other out. The Ks cancel each other out. So you have 0.36 divided by 0.18 is equal to 0.2 to the y divided by 0.1 to the y. So now we plug this in, and now we've got 0.36 divided by 0.18, that's 2. 0.2 divided by 0.1 is 2. So 2 is equal to 2 to the y power. Well, what's 2 to the y power? Y has to equal 1. Guess what? We found the rate, we found the order for the CL2, and it's 1. So we found x and y. We found it. We now have the rate equation. We can now figure out what's our proportionality constant here. We can finally figure this out. We have our NO2 from our first thing. We have our CL2 from the second thing. So now, as we're wrapping up here, we're going to find K now. And the reason we can find K is because we have the rates. We know that NO is going to be squared, whatever the concentration is going to be, and the CL2 is going to go to the first power anyways. So the beautiful part about this is we get to pick any trial for our data and plug it in, because it won't matter which trial you pick. It's awesome because, guys, you will come out with the same number. Yay! Exactly. Yay. Okay? So we're going to go and look at trial number 1, where both initial concentrations are at 0.1, okay? And we've got 0.18 as our rate that we have, because K will equal the rate divided by the concentration of NO squared multiplied by the concentration of Cl2 to the first power. So now we plug all this in and we end up getting 180 liters squared times moles to the minus 2 times seconds to the minus 1. So another way to look at this is 180, okay, molarity squared per second. This is another way of writing this. And honestly, when you look at the units there, you don't really panic too much about that. Okay? Now, we have one more slide to go through. And we're looking at, well, what's the overall order of this reaction? Well, let's take a look at it. The overall order of the reaction is the sum of the reaction orders that we calculated earlier. You might remember that. So here we have NO squared. We calculated that earlier. We have the concentration of Cl2. We also calculated that earlier. So we have a 2 and a 1. So let's check this out. The overall order is 2 plus 1 is 3. That's it. It's a third order. It's a third order reaction. And that's it, ladies and gentlemen. We finally come to the end of the road. We worked through one kinetics problem where we were able to figure out what exponents were needed to be raised for the individual starting reactant concentrations. Once we found those by comparing the rates, then we went ahead and found the proportionality constant for the end. So, ladies and gentlemen, I hope this will help things out a little bit, and I will see you the next time.